This is Song Liu from University of Bristol. So to some of the attendees, probably you already know me because I both worked in the Institute of Statistical Mathematics as well as Bristol. So today is really a nice occasion that we have Professor Hideitsu Hino to give us an interesting talk on model principal component analysis. Really looking forward to the talk. And if you have any questions, please feel free to type your questions in the chat. And later, Hino-sensei will answer your questions after your talk. Is that okay? Okay, good. Good. So without further ado, let's welcome Hino-sensei giving his talk. Please.
Thank you for kind introduction. I'm Hideitsu Hino from the ISM Japan. Okay, so today, sorry. Okay, I'd like to talk to you about model principal component analysis. This is a joint work with Mr. Keiichi Sando from University of Tsukuba. Okay, so let me start with the background and the notation for the principal component analysis. Maybe there might be no need to explain in detail, but PCA is, say, indispensable for data analysis. And in this talk, we use borrowed X for the d-dimensional random variable with the probability density function f sub x of x. And by here, f sub v transpose x of x, the probability density function of the random variable v transpose x. I mean, this is a projection of the random variable x by vector v. And D is the set of realizations of x. I mean, this is the observation. Okay, conventional or classical principal component analysis finds the projection axis by maximizing the empirical variance. By principal component, we indicate the direction on which the projected dataset has maximum variance in this direction indicated by red line. And on the other hand, by the minor component, we indicate the direction with minimum variance in the framework of classical PCA. And PCA is very important and widely used, but it is notoriously sensitive to outliers. You know, the red line here is the principal component, and with only small amount of outliers like this, it can be significantly deviate from the true direction. Here, it would be better to formally define what is the outlier when we consider robust statistics, but I think formal definition of outlier is difficult, and maybe there is no consensus. One of the standard ways of defining outlier would be, say, considering a mixture of majority and outliers. But here I use say rather sloppy and intuitive definition. Outliers are observations that are at abnormal distance from other values of population or majority. Anyway, it is important to consider the robust version of PCA. And there are, of course, many robust PCA methods. And in this talk, I introduce a novel method based on the notion of mode. The minor component in classical PCA was direction on which variance is minimized. This is a minor component in classical PCA. And the use of the empirical variance makes the classical PCA sensitive to outliers. So as an alternative, we need a quantity which take a large value when sample is concentrated on small region, like the inverse of variance. And at the same time, unlike the variance, the quantity should be, say, robust to outliers. And here I propose to use mode as an alternative measure for concentration. Mode is, as you know, robustly characterizes the location of the maximally possible values. This is very simple example of mode for a highly skewed distribution. The yellow line here is the mode, and the red line would be a median, and the blue line is mean. So to characterize this kind of distribution, mode is better than other two location parameters. And there are many mode estimators, but here we consider the one based on the so-called Parson-Rosenblatt kind of estimators. And we propose the modal principal component analysis as a robust variant of PCA. And the model PCA or MPCA is formulated as an optimization problem with respect to both the projection vector V and the mode M of the data projected by the vector V. And V is a projection vector, so it is constrained to the unit sphere. And here, phi h is a kernel function with bandwidth parameter h. And in this one, we consider a standard Gaussian kernel function for this Gaussian kernel function. And we start from the first minor component V1 by solving this optimization problem without considering this constraint. And then we remove the obtained minor component from the given data set and find the second minor component with the orthogonality constraint to the first one. And by repeating this procedure, we can find k minor components, and as orthogonal complement of the span of the minor components, we get the principal subspace for visualization or concise data description. Okay, my main focus of interest in this talk is the theoretical properties of the projection vector or minor component obtained by solving this problem. And in this talk, we only briefly explain how to solve this optimization problem. I will come back to the problem of how to solve this problem later. Okay. About the solution of the model principal component analysis problem, we got these three results. The first is uniform convergence property, and the second is inference function, and the last one is the lower bound of the breakdown point. Okay, let me start with convergence property. Okay. Under standard regularity conditions, we can prove this uniform convergence in probability. This theorem states that the value of the density function estimated by using Parson-Rosenblatt estimator at any point on any direction get close to the value of the ground truth probability density function of the data projected to the direction of V in probability. This result justifies the in a sense our optimization problem for finding the minor component based on the notion of mode. I mean, it can be seen that for any direction and any point, this kernel density, kernel mode estimate is will converge to the true one in probability. Maybe this result can be seen that textbook example on the convergence of the kernel estimation for mode. But it is not the case because we consider both estimation of mode and estimation of projection vector in joint manner. So the proof will require a bit involved techniques. I don't explain in detail here. Okay. And we also have a theorem on the convergence rate. In addition to the standard regularity conditions in the previous theorem, we assume the rate of decrease of the bandwidth of the kernel function. Then the rate of the uniform convergence is of order n to the minus 1 over k, which is the same order of the decrease of the bandwidth parameter. This rate is not very fast compared to the already known standard rate. I'm sorry, I don't remember exactly, but the conventional standard rate for this sort of mode estimation is something like log n over n to the power 2 over 5 for example, for twice differentiable functions. And this is because we have to consider uniform bound with respect to both m and v, I mean the mode and the projection vector simultaneously. Okay, these are the result for convergence property, and our next result is our derivation of the the inference function of the estimated minor component vector. That is, we can evaluate the effect of an outlier to the case minor component. The inference function is theoretically important to characterize the robustness of estimators, and it also plays an important role in the theory of linear estimators. The inference function has several different definitions, but here we adapt this definition. It is defined by the derivative of the estimator t in the direction of the outlier u, where the delta u denotes the Dirac measure, and f is the population distribution. Okay, with straightforward but somewhat bothersome calculation following the definition, we get the inference function of the minor component estimated by solving the this optimization problem for the proposed minor component, modal principal component analysis. And these are the counterplot for the inference function of the minor component obtained by this one is from classical PCA, and this one is for a model principal component analysis. We consider two-dimensional Gaussian distribution centered at the origin and with the diagonal covariance matrix. And it is seen that the value of the inference functions of the model PCA is are far smaller than those of the classical PCA, and it indicates that the robustness of the model principal component analysis to any outlier u. Okay, unfortunately, the inference function is only calculated by using the grand truth probability distribution of the population here, f. I mean, we do evaluate the inference function, we need to know the ground truth distribution F. So it is theoretically important, but in reality, it is difficult to compute the inference function by using only the observed dataset. So I think the most important contribution of our work is the derivation of the lower bound of the breakdown point. The breakdown point, or the finite sample breakdown point, is the number of outliers that estimator can accept or tolerate. And its lower bound provides a kind of, say, worst case evaluation for acceptable contamination. So in standard definition of the breakdown point for statistic T, we consider the amount of outliers that can make the absolute value or norm of the statistic T infinity. But we are considering the projection vector, I mean V, and this is normalized to have a unit norm. So we cannot use conventional definition of breakdown point. So we introduce the a variant of breakdown point. I mean the angular breakdown point for projection vector. This is a definition of the angular breakdown point, and it says that basically, suppose we have a set of observations y. Observations are of size A. And using this dataset YA, we got the estimate of the projection vector V hat of YA. And then suppose we can add B extra dataset and makes the estimate of V orthogonal to V hat of YA. The minimum of such B over A plus B is a breakdown point in this case. It means that how many outliers are required to make the estimate of the projection vector to turn to a completely different direction. Okay. You can get the intuition for the breakdown point with this simple example. When we have only inliers, the principal component direction would be like this red line. And with small chunk of outliers over the population of inliers, the principal direction does not change, fortunately in this case. But when the amount of outliers get larger, the say, how can I say, variance maximizing direction would be vertical to the true vertical to the line along with the population in layers. And this case, the estimated principal direction here is completely breaks down. Of course, this is a kind of, say, extreme case and very simple toy example, but anyway, the breakdown point characterizes the robustness of the statistic to the contamination. And again, unfortunately, it is in general difficult to calculate the value of the breakdown point without knowledge of the ground truth probability distribution of the inliers. However, for the estimate of the first minor component, we can calculate the lower bound of the angular breakdown point by using the observed data only. This theorem states that for the estimate of the projection axis to the first minor component, we get the lower bound of the angular breakdown point by using the observation data. I mean, you know, we can evaluate this B star with the given, only using the given dataset. So, we note that in this theorem, YA, it should be clean data, I mean, without any outliers. So, as the use case of this lower bound, I think we can use this by, say, we firstly collect a small amount of clean data and estimate the lower bound of the breakdown point to know the ratio of outliers allowed to be mixed with clean data. Okay, so we can evaluate how many outliers can be accepted or acceptable for applying the proposed modal principal component analysis by using this theorem. Okay, let me show a simple experimental result to see that the lower bound with the breakdown point captures the tolerance of the estimate. I'm sorry for my poor drawing, but I feel it is easy to explain the this experimental setting with this handwritten picture. Okay, we consider say 500 inliers, which forms a very slender ellipsoid centered at the origin and of three-dimensional space, and it is sampled from this normal distribution. I mean, centered at 0, and the variance for x1 axis is 1, and the x2 axis is 0.3, and the variance for the x3 axis is sigma z, which is far smaller than 0.3. So the principal component obtained from this data should be this direction, 1, 0, 0, right? And because sigma z is very small compared to 0.3, the minor component should be 0, 0, 1 in this vertical direction, direction to the x3 axis. Okay, and for this, say, inlier datasets, we add a chunk of outliers drawn from normal distribution with mean 0, 0, 150, with variance for each direction 0.1, 0.1, and sigma z. Here, sigma z does not have significant meaning, and just for giving, say, a perturbation for the data distribution. The important thing here is the ratio of the outliers, and it is controlled by the parameter alpha, ranging from 0, I mean, inlier only case, and 0.5. Okay, and when the alpha gets larger, the minor component estimated from the whole sample, including both inlier and outlier, would be changed to, say, this direction. I mean, 0, 1, 0, this MC dash. And this is orthogonal to the original minor component, 0, 0, 1. So in this case, completely, the estimate of the minor component completely breaks down. It is difficult to directly control the value of the lower bound of the breakdown point, so we varied sigma z, I mean the variance in the x3 direction, to perform experiments for different experiments with different lower bound breakdown point values. And we ran with 100 independent row of observations, and shows the result, shows the box plot of the cosine to the true and estimated first minor component directions estimated by our proposed MPCA algorithm. So, I mean, when the cosine is close to 1, the minor component is well estimated, and the cosine is when close to zero, the estimated direction is almost orthogonal to the ground truth. And the lower bound of the breakdown point is calculated by using, I'm sorry, I don't remember exactly, but maybe 50 in layers in advance, and shown with the vertical red line here in this plot. And it is seen from this plot that around the contamination ratio is about 0.28. 0.28 in most of the trials, the estimated minor component is orthogonal to the ground truth. And of course, our estimated lower bound of the breakdown point is 0.09 in this case, and yeah, this is smaller than 0.28. And we change the parameter sigma z to change the value of the lower bound of the breakdown point. And in this case, the value of about 0.2. And in this setting, it is luckily quite robust, and almost half of the datasets can be outliers. But anyway, it is seen that with the increase of the rate of the outliers, the possibility of failure also increases. And the generation of the estimation is notable around the outlier ratio is about 0.4 or larger. And this is larger than the estimated LBPP value, 0.2. So yeah, we can use this lower bound of the breakdown point as say pessimistic evaluation of the acceptable outliers. Okay, we also performed a comparative study as a robust PCA methods for the problem of say subspace identification. We use several standard multidimensional datasets downloaded from UCI machine learning repository, and these datasets originally for classification, but for each dataset, class with the smallest number of sample point is treated as outliers, and we consider the ground truth say principal subspace is the subspace found by using classical PCA for in-layer only. And the dimension of the principal ground truth principal subspace is determined so that the contribution ratio of the eigenvalue of the PCA is around 99%. And then several PCA-like methods are applied to the whole dataset, including both in-layers and outliers, to find the principal subspace. The spectral distance defined here between the obtained subspace and the ground truth subspace is compared. We measure distance from the ground truth, so the smaller the better. The ground truth principal subspace is defined by using classical PCA, and so in this sense, this experiment is advantageous to classical PCA. But anyway, from this table, the proposed MPCA is say it's fair to competitive to other robust PCA methods. Okay, let me summarize my talk. We propose the dimension reduction the proposed dimension reduction method is robust because it is based on model estimation. The proposed method is theoretically shown to have some good properties. I mean, the convergence to the ground truth density in probability, and we derive the inference function, and we also derive the lower bound of the breakdown point to characterize the robustness of the proposed method. And actually, it is difficult to clearly state for what kind of data the proposed method is suitable. It is always difficult when we develop a novel method. And I think it's just a conjecture, but I think I remember that conventional PCA works perfectly when the data is Gaussian without outliers, because Gaussian is completely characterized by say up to second order moment, I mean variance. And PCA is based on variance, and this justifies the complete success of the PCA, I mean classical PCA for Gaussian distribution. And our method is based on model estimation, and it would work nicely when the model estimation is easy. For example, in I'm sorry, I didn't show that result in this talk, but you can see the experiment in my journal paper or paper on archive. Anyway, in our preliminary experiments using artificial data sets generated from Gaussian and Laplacian distributions, the performance of our method in Laplacian case is very nice compared to Gaussian case. And I conjecture that it is because Laplacian distribution is more peaky than Gaussian, and finding mode for Laplacian is a relatively easier task. So the ease of estimating mode for the underlying data distribution would be the important point. And of course, there are both pros and cons for the proposed method. And unfortunately, the proposed method is, say, intrinsically slow because it finds a principal component by removing minor component one by one. And maybe it can be improved by deriving sophisticated optimization method to some extent, but yeah, I have to say that our method is not appropriate for very high dimensional data. Oh, sorry, I didn't explain the optimization method for the proposed objective function. So let me briefly explain. There must be many approaches, and unfortunately, I'm not very familiar with this kind of optimization problems. So I solved the problem in rather, say, a naive way. It is an optimization problem with respect to M mode and V projection vector. It is, yeah, as simultaneous optimization seems to be quite difficult. So we iteratively solve for M with a fixed V and solve for V with a fixed M. And for optimizing M fixing V, it is easy because this is just a model estimation, and there are robust and computationally efficient methods. And in our implementation, we use the so-called say half sample model estimator proposed by Becker and Ruiworth in 2006, and this is something like a bisection search method. Okay, and for optimizing V fixing M, it is a bit involved, and so we consider the logarithm of the objective function. This logarithm of this objective function, and using the Jensen's inequalities and assuming that this kind of function is Gaussian. then the problem is simplified to the minimization of the squared loss. But difficulty remains because the vector v is constrained on the unit sphere and must be orthogonal to other projection vectors. But fortunately, by changing the coordinates appropriately, we can reduce the problem to unconstrained problem. And that reduced unconstrained problem is solved by using the conjugate gradient method. So please please read the paper in detail of the optimization algorithm. Okay, so I already told this discussion part. So sorry, yeah, that's all. And okay, I'm open to your questions. So let me check the questions raised by audience.
Yeah, so there have been some questions. Yeah, so please.
How strong is the differentiability condition? First of all, Song raised their question on the smoothness of the, you mean the smoothness of the probability density function?
Yes,
right?
So let me elaborate a little bit. So for example, you mentioned the Laplacian distribution in the end, and that is not differentiable at the peak, right?
I see.
And that's one thing. Another is the concept of mode is not well defined on discrete data sets, right? So like, for example, PCA finds the direction maximizes the variance, but variance is well defined on discrete data sets. So I'm wondering how well this kind of mode notion would work on discrete data sets.
Okay, so first of all, unfortunately, the proposed method is not intended to be applied to a discrete dataset. So I think, because of the reason you explained, and yeah, I applied the method to several discrete dataset, and it works nicely in reality. But theoretically, it is not for a discrete dataset. And as for the differentiability of the ground truth distribution, when we prove the, say, convergence and in probability and the convergence, deriving the convergence rate, I think we do not impose the differentiability conditions on the probability density function. We only assume that the kernel function is smooth and differentiable. And I think this would be the result, the reason that we got the satisfactory result for Laplacian distribution.
I see. Yeah, thank you very much.
Thank you. And the next question is raised from Professor Fukumizu. In practice, how can we use the low bound of can we use it to compare the robustness? As for the lower bound of the angular breakdown point, let me show the slide again. You know, this lower bound of the breakdown point is can be computed by using the observed clean, in-layer only dataset. So if we want to evaluate how robust the estimated minor direction by using the proposed method, we firstly carefully collect small amount of clean data and estimate the lower bound by using this theorem. And we can say that at least the the estimated minor component, or I mean, at least, we know the ratio of the acceptable outliers by using this theorem. Is it? Am I correct?
So yeah, we may be able to estimate it, but the question is, what's the definition of outlier in practice? Do we have some models? In the case of standard PCA, we have some models like Gaussian.
Yes, that's
yeah. What is a true and what is an outlier?
Yeah, it's a very important, but during this work, I avoid explicitly defining the outliers and in this model, and I'm still struggling to find what is a proper definition of outliers in this model, but currently I have no crisp answer.
So in this case, you are not assuming that the true one is unimodal. True one may have multiple modes, right?
May have, yeah, but the mode, the mode should be unique. Of course,
unimodal. The density should be unimodal.
Mode, the distribution can be multimodal, but mode can be, mode should be unique. Say, for example, we have a mixture of two Gaussians, but the one should be higher mode than the other one.
I
so
see.
In this sense, the mode
point should be unique.
Yeah.
Okay, I see. Okay. That's an outlier, but that allows the multiple modes. I mean, that's a multiple peak points, and their outlier gives another mode maybe. And
you're right.
It's not easy to say which is true and which is outliers in practice.
Yeah, you're right. And maybe I should discuss by using very low dimensional examples, but currently I don't find which is the proper definition of the inlier and outlier.
Okay, so in extracting multiple dimensional subspace, you are still focusing on the highest point, not the second or third mode.
Only highest point.
Okay, yeah. I see. Okay, I see. Thank you.
Okay, and next question is raised by Daniel. Can you describe the decomposition in terms of within cluster? This would be related to Kenji's the discussion with Kenji. Is it right?
Yeah, that's right.
Daniel is anxious about the case with multiple mode or multiple chunks. And my answer is currently I have no idea how to deal with such a such situation. Of course, the real data, including the ones are used in experimental evaluation, would have multi-mode or cluster structure. And empirically, it works to some extent, but actually, currently I have no idea for how to deal with cluster structure and the data.
Okay, thanks.
Thanks. And can you have another question? Can we theoretically compare the method with R? Okay, as far as I read the related works, I couldn't find the robust, I couldn't find, say, the inference function or breakdown point analysis for conventional robust PCA method. And as far as I know, most of conventional methods focus on the, say, identifiability of the true grand truth subspace based on certain, say, certain model or certain definition of the inliers and outliers. So the same kind of analysis is, as far as I know, there's not so many the same kind of analysis. And, okay, and the question raised by Song is, how sensitive is this method affected by the choice of H? I can. Yeah. I didn't mention the how to select the bandwidth H, and theoretically it should decrease with certain rate, and in reality, yeah, of course, their choice of the bandwidth plays a very important and critical role for the performance, and we can apply any of the conventional bandwidth selection method, but we have to optimize, or we should optimize the bandwidth every time we consider different direction. Direction. I mean, the projection. When we change the projection vector, the appropriate bandwidth would change. So in the implementation, we use very simple rule of thumb. I don't remember exactly, but yeah, I adapt a very computationally efficient bandwidth selector, and for each iteration of the update of the projection vector, we estimate or we select the appropriate bandwidth H.
Can I just ask one quick follow-up question?
Okay.
So you mentioned that the H should reduce as number of samples increase, right?
Mm-hmm. Yeah.
So could you briefly explain why so in the sense of or in the context of mode PCA?
The estimation of mode is based on the standard Parson-Rosenblatt estimator, and in the theory of standard kernel density or kernel mode estimation, the bandwidth should decrease here.
I see. Okay.
So
yeah.
Okay, and the final question is okay. Sample code. Yeah, every experiment, including a toy example and for comparative studies, and including other compared robust PCA-like methods, you can find Julia implementation from my website. And we also have R implementation, and if you prefer R implementation, please mail me. I will, yeah, I can give you to reproduce the code to reproduce all results. Leo, is it okay?
Yes, thank you very much.
No problem.
Yes.
Okay, I think that's all the questions. So thank you so much for Professor Hino's interesting talk, and I really enjoyed this topic. And thank you also to all the attendees attending today's talk, and we will resume next week. So Patrick and I, we will give 2 talks next week. So thank you again, Professor Hino. Let's do
thank you.
Virtual.
Thank you for stimulating questions, and the discussions.
Yes.
Yeah.
No
Thank
problem. No problem. Okay. So have a good day or have a good night.
Have a good night. See you next week.
Bye-bye.